Anyone need the note packet for chapter 4? I have quite a few photocopies here. That leads me to think that somebody needs it. Anybody else need the chapter 4 notes packet?
Yeah.
Okay, Josh, you need it? Chapter 4, okay. All right. Then let's review how to find information in a rational function. So I'm going to start by writing down a rational function. We'll start by having f of x equals something simple like this, and then all over third plus minus 15, that's nice. Okay, so here's our rational function. Rational because it's a ratio, because it's fraction. And the first question is, how do you find the y-intercept of this function, let alone any function? How do you find a y function or a y-intercept of any function? How do you find the y-intercept? I think I'm hearing it. Yeah, just plug in 0. Plug 0 in there, and then you get your y-intercept. So I'm going to put the y-intercept as f of 0. And so in this particular case, if I plug in 0 for x and I plug in 0 for all those x's, all you're left with is the plus 15 over negative 15, and that simplifies to just negative 1. So in this case, the y-intercept would be negative 1. Okay, how do you find the x-intercepts? And I should start by saying, what's the very first thing we always have to do to a rational function? It is factor it. So you go to town factoring. So this one would be x plus 5 over x plus 3, and then x plus 5 over x minus 3. So, okay, so we factored it. So then where are the x-intercepts? You have the top, the numerator. So when you set each of those factors equal to 0, you get the x-intercepts. All right, so there's the x-intercepts. And then how do you find the domain of a rational function? The domain always begins, the domain is all real numbers in the world except for, yeah, anything that would cause you to divide by 0. So you'd set that equals 0, that's negative 5, that equals 0, that's positive 3. So first of all, the denominator, first of all, you might just say has the domain exclusions. So there's our domain exclusions, which are x equals negative 5 and 3. And the domain exclusions come in one of two varieties. So let's keep reading here. How do you find, how do you find the holes in a rational function? Yeah, exactly right. So these two cancel out, and so that represents a hole. And so we have a hole at x equals negative 5. So that was a domain exclusion. We're not allowed to plug negative 5 into this function because it would cause you to divide by 0. And graphically, what you see at x equals negative 5 is a hole. All right. And then how do you find vertical asymptotes? Where are the vertical asymptotes?
The vertical asymptote is the remaining denominator. Yeah, anything else that doesn't cancel out from the denominator. So in that case, this one right here is a vertical, I'm just going to write VA for vertical asymptote. So I have a vertical asymptote at 3. And then finally, how do you find the horizontal asymptotes of a rational function? What's the ratio? Yeah, the ratio of the leading terms. So you take the ratio of the leading terms. So the ratio of leading terms will give you the horizontal asymptote. Oh, there we go, horizontal asymptote. By the way, just to finish this graph, the x-intercepts are always when f of x is equal to 0. You solve for x. Okay, so that's a goodly amount of information to just be able to look at and see and read off of the function. And again, remember, probably like the underlying theme of this whole course or any math class is to be able to, on the one hand, look at the function and say what the graph would look like, and or to look at the graph and say what the function would look like. So we're constantly trying to go back and forth between those two things. Just by looking at this function, I know a lot about what the graph looks like. And or if I were just to look at a graph, I should be able to work backwards and figure out what the function looks like. And that's our main goal. All right. Well, good morning, folks. Happy Monday. Next week, oh my goodness, we have spring break. How sad. A whole week where you don't get to go to class. Would you all like to sign a petition with me, and we'll petition that they do not have spring break and we continue taking classes as usual? Would anyone sign that petition? No, sounds not like it. Okay, well that's fine. So we'll all just take the week off of school. During that week, you can study, you can email me, and then when we come back on that Monday, we have a test on chapters 3 and 4. All right. So this week, today and Wednesday, we're just going to keep on moving along through chapter 4. A lot of exciting things in chapter 4. Part of it is just knowing how to graph a rational function, but then we'll also see how to solve rational equations, which I think we'll get to start today. All right, I have a joke for you. Why can a nose not be 12 inches long? Because then it would be a foot. A knee slapper. All right, here we go, folks. We started here, right? And I think we got all the way through number 3. Did we do number 3? Yeah. No, not 4.0. We're completely skipping 4.0. You don't have to do 4.0. Yeah, we did number 3. All right. Number 4, I have blue boxed out, so we're not going to do number 4. Let's go ahead and take a look at, ooh, number 6, I put a star next to it. That must make it a really good one. So you can leave number 5 as homework for yourself, but let's do number 6 together. And we'll walk our way through all the steps and remind ourselves how to analyze a rational function. So f of x equals x squared plus 2x squared. Oh, x cubed. There we go. X cubed plus 2x squared plus x all over x squared minus x minus 2. Okay. So, are they really?
Yeah.
Oh no.
We have 3x squared minus 5x minus 2 over.
And that is number 6. Oh. Well, I wonder if that.
Number 5 is the same. That's number 7 for us.
Oh, it is? Oh, I wonder how I did that. And I don't even have number 7 up here. Oh. How tragic. What comes after 7, 8, and then and then we start 4, 2. Okay, well then I'm gonna write down what you have. Sorry. Oh, there's all relative as well. Okay, well then the next one we would do is number 5. And number 5 is the same?
Yes.
Okay, well then we'll do number 5 and then I'm gonna write down number 6. So it's actually, 1 second, Abe, let me write that down. Oh, actually, Abe, I have an extra copy right here. I'll just look at this. Sorry about that, folks. All right. Let's start with number 5 then. I'll just hold my little paper up here. So number 5, we have, and while I'm writing this down, go ahead and start looking for information. Look for information in the way we just did. What would you do? So we have this is a better starting point anyway. Okay. What information can we find just right now without doing the factoring first? What information can we get without doing any factoring? Yeah, we can find the y-intercept by just plugging in 0. So let's go ahead and do that. I'm going to find my y-intercept, which is actually f of 0. And if I plug in 0 everywhere, I end up with negative 12 over negative 6. Does everyone see that? That if all those other terms become 0, you just have those last 2 terms at the end. So my y-intercept is at 2. And what's the other piece of information I have without doing any work, just looking right there? There's one other piece of information we can get before we factor. Yeah, the horizontal asymptote. I can make the ratio of those leading terms. And that would give me 1x squared over 1x squared, which is really 1. So my horizontal asymptote is at the horizontal line, y equals 1. So that's what we have so far. I'll start my graph. I can say that I have a y-intercept at 2, and I also have a horizontal asymptote at 1. 2, at 1. That's what I know so far. Okay, now that's just the information you can get by looking at your function without doing any work. Now, what's the work we have to do? Yeah, now we just have to factor it. So I'm going to go ahead and rewrite this then. So f of x is equal to 1 multiplies to make 12, that adds to make negative 1. X minus 4x plus 3. And then on the bottom, 1 multiplies to make 6, that adds to make 1. Yeah. Write that down as x minus 2 and x minus 3. There we go. So we factor our expression. The 3's obviously cancel out the x plus 3, so that's my whole at x equals negative 3. And then the factor at the bottom that didn't cancel out, that's my vertical asymptote at x equals 2. And once you do that analysis on the denominator, then go ahead and look at the numerator. The only x-intercept that we actually have is x equals 4. So I have an x-intercept at x equals 4. Why don't I have an x-intercept at x equals negative 3?
Because the numerator.
Yeah, they canceled out. So there's actually a hole at x equals negative 3. If I just looked at the numerator first, I would think that there's an x-intercept at negative 3, but there's no x-intercept at negative 3. Because in fact, there's a hole in the graph at x equals negative 3. All right, so that's what we have so far. Let's draw that onto our graph. So I have a vertical asymptote at 2. Here's my 2. I have a hole at negative 3. I don't know where that hole is yet. And then I have a vertical, I have the vertical asymptote. The x-intercept is at 4, so 2. There. All right, looking good. That's what we have so far. Now you'll notice I wasn't necessarily following along with what the instructions asked us to do. Let's finish up and I'll go in order here. So find the domain. Well, first of all, the domain is that x can't equal 2 or negative 3, because that was my vertical asymptote and that was my hole. That was part A. And then part B, identify any vertical asymptotes. We did right there, x equals 2. Identify any holes in the graph. We did right there. That's x equals negative 3. Find the horizontal asymptote. We did that. The horizontal asymptote was y equals 1. Find a slant asymptote. There isn't one. You either have a slant asymptote or you have a horizontal asymptote, but you won't have both. You'll have one or the other. And then it says graph the function. Okay, well, we're almost done. So how do we draw in the rest? For any rational function, you will tend to have a graph that has 2 swoopies, one in the upper right or one in the lower left. Or those swoopies could be reversed and you'd have one in the upper left and one in the upper right. So those are the 2 different possibilities for just a normal standard rational function. There's a lot more possibilities than those, but those are just the usual ones if there's only one vertical asymptote. And indeed, we only have one vertical asymptote. So which one of these would be our drawing? One on the right or the one on the left? Which one matches the y-intercept and x-intercept that they gave us? They're the one on the right. So I can kind of casually now go ahead and come in here and put a vertical asymptote, go through that point, horizontal asymptote, come up here, vertical asymptote, and then go through that point, and then horizontal asymptote. And that is what my graph would look like. And furthermore, now I can draw my hole. I have a hole at negative 3, so negative 1, 2, 3, and I'd have a little hole in there. My graph. And that's our rough sketch, right? And I don't know, maybe you're looking at that thinking, golly, Mr. G, this is a little too casual for me. I mean, we just drew some swoopies on a graph. You know, what confidence do we have that that really is what that looks like? Well, let's look. If we now go, where's Desmos? Go, now let's actually graph this thing. X squared minus x minus 12 divided by x squared plus x minus 6. And sure enough, this is what our graph looks like. We did have a vertical asymptote at 2. We did have a horizontal asymptote at 1. And there should be a hole at negative 3. Oh, look at that. Does everybody see the hole? I can make this bigger. Yeah, that's better. Yeah, there's our hole right there at negative 3. So does our graph have all the details that the Desmos graph has? That's looking pretty good. All right. Questions, folks, before we move on? Go through that analysis. Then let's see here. Without necessarily doing completely all of the following problems, let's at least factor them and identify all the information. So like for instance, your number 6, I'm going to write down what you have, not what I have on the board. So our function is 3x squared minus 5x minus 2 all over x squared minus 9. So again, I think it'd be helpful to start with the information that we can see already without factoring. So what are the 2 pieces of information we can get without factoring? And we get the y-intercept pretty easily. So my y-intercept is f of 0, which in this case, all x terms go away. I have -2 over -9, which is just positive 2/9, or 0.2 repeated. And then what's the other piece of information that we can get? Yeah, we can do our ratio of leading terms. So 3x squared over 1x squared. So my ratio of leading terms is 3x squared over 1x squared. The x squared terms cancel out. You just have 3 over 1, which is really just 3. So my horizontal asymptote is y equals 3. And at that point, you could begin your graph. You can say, well, my graph, I will have my y-intercept at 0.2. Now, where do you draw a y-intercept at 0.2? You know, like if you have your tick marks, 1, 2, you're just putting a dot, just barely above 0. It's just an approximation. And then we have a horizontal asymptote at y equals 3. Oh boy, my graph. There's my 3. Should probably scoop my whole graph down. I'm going to do that again. I'll bring that graph down. 1, 2, 3. There's my y-intercept. And there's my horizontal asymptote. All right, then what do we do? And now we get to factor. So the bottom is pretty simple to factor. How does the difference of squares, x squared minus 9 factor out? Very good, x plus 3, x minus 3. And then on the top we have 3x squared minus 5x minus 2. That particular problem, I would do a little scratching work, just off to the side there. And how do you factor 3x squared minus 5x minus 2 when the leading term is not a 1? If the leading term was a 1, we could say what multiplies to make 2 to make 5, but that actually doesn't work. So what do I have to do with the 3? Yeah, we do the 3 over there by the 2. So 3 times -2 is -6. Our factor table for 6 is 1 and 6, 2 and 3. We're multiplying to make a -6. That's a positive and a negative. And we want to add them together to make -5. 1 plus, 1 minus. So it'd be the 1 and the 6. What, a positive 1 and the -6? Then what? Our answers are not just 1 and -6. We have to do what special thing? We're going to do what? Yeah, factor by grouping, exactly right. So I'm going to rewrite -5x as 1x minus 6x or minus 6x plus 1x. I'm going to write down 3x squared minus 6x plus 1x minus 2. So we just rewrote the middle term. That's actually the whole point of a problem like this, is to multiply the first term times the last term to find out what term is multiplied to make that number, that adds to make the middle number, so that you can rewrite the middle number, and then you can actually factor by grouping. So over here, we can take out a 3x, leaving behind x minus 2. And here we can't factor out anything. And when you can't factor out anything, you just put a 1 in front. You put a 1 out front so that you can still see that there is a number there. And, yep, that's why. So both of our parentheses are both x minus 2, so that's one of our terms. And then the rest is 3x plus 1. And that's really why you put the 1 out front, so it's more obvious what goes inside the other parenthesis. So we have successfully now factored the numerator, x minus 2 and 3x plus 1. Does this rational function have any holes? No holes, because nothing canceled out. That's interesting. Because there are no holes, we now have 2 vertical asymptotes and 2 x-intercepts. Because there was no hole, we have a lot more information. So we have a vertical asymptote. Here, I'm going to put that down here. So I have vertical asymptotes in the bottom. So that's at x equals -3 and at x equals +3. And then we have our x-intercepts up in the top, which the first one's simple. The x-intercept is a 2.
And then the second one, you have to solve 3x plus 1. Yeah, you get 1/3. And I would write it down. I would say, okay, when does 3x plus 1 equal to 0? And then do your basic algebra to see that 3x equals -1, divide by 3, and get x equals -1/3. So now we have my x-intercepts at 2 and -1/3, and my vertical asymptotes are plus and minus 3. Okay, now, once we write that in, 1, 2, 3, that's -3, there's my vertical asymptote. And then 1, 2, 3, that's my vertical asymptote. And I had an x-intercept at 2, as well as at -1/3, which, where's -1/3? It's just off to the left a tiny bit. Now, did we finish our analysis? Find the domain. The domain is just not 3 or -3. So we talked about the domain. X is not equal to 3 or -3, because those are vertical asymptotes. Identify the vertical asymptotes, we did. Identify the holes, we did. Find the horizontal asymptote, we did. No slant asymptote, and then graph it. Now, looking at this so far, this graph, we do not have any knowledge off the top of our head to say, oh yeah, draw some swoopies here, here, and here. We just don't know. So at this point, you'd have one of two options. You could either make a table of values, which would be very exciting, and you will get to do that on the test, is they'll say make a table of values. And so on the table of values, you just want to find a couple other points so that you can generally see where the swoopies are going. So I would choose some points off to the left of -3. Like I'd probably do a -4 and a -5 on my table of values. And then I'd want, well, I already have 3 points in the middle here, and it looks like the graph is going like this. Now that's a big assumption, isn't it? We'd probably choose one more point, maybe a -2. Then we'd have another point there. And we need some points over here to the right of 3, maybe 4 and 5. So that would be the table of values I would do. I'd plug in all those values for x, and that would give me some points to plot and see where the rest of the dots are. I'm going to demo this in front of you here. So we want to plug all those inputs into our function so that we can have some more dots on the graph. And then we'd be able to better see where to trace in our lines. So let's see here. What I'm going to do is plug this function into my graphing calculator. So I'd go to y equals, plug in 3x squared minus 5x minus 2 divided by x squared minus 9. Now, of course, at this point, I'm about to see the graph. And that's going to give away what the graph looks like. 3x squared minus 5x minus 2. Oh, I didn't write it. X squared minus 2. Or, yeah, I can just go to my table. You hit second graph, or there's a table there. And I'm going to get my values from my table of values. So I've got a point at 6.125, and then at 9.4, at -4, and then at 3.7 and 3. So folks, in case you've never tried it before, on your graphing calculator, instead of hitting graph, right above graph, you hit second graph, and there's a little yellow word or a blue word that says table. And so I just went into the table. And in fact, then you don't have to do any calculations. You don't have to plug any of those manually into here. You can just use your calculator to make a table. And once you have that table, now I can go and plot its 4 points. So at -5, I'm up at 6, which is not there. At -4, I'm at 9, which is up above it. And then at -2, I'm at -4, which is down here. And at 4, I'm at 3.7, which is about here. And then at 5, I won't. 5? Oh, okay. So it comes down below. Then it comes back up. Yes, it does. Oh, well, that's very surprising. Okay, so now we have a couple of points. Now I'm going to take a look at my graph real quick just to confirm what is happening there. Yep. All right, so this part is a swoopy that looks like this. But it's vertical, it has a vertical asymptote going up and a vertical horizontal asymptote going to the left. This part down here, sure enough, looks like a really weird upside down parabola. It's not a parabola, it's just an upside down curve. And then over here to the right, it comes down below the asymptote, but then comes back up and levels off at the asymptote.
And that's what our graph looks like. At this point, it wouldn't hurt to show that on Desmos so everybody can see the real deal. So I'm going to type in 3x squared 5x minus 2 and x squared minus 9. And my asymptotes, 3, -3, and a the y, that was a 3. There we go. All right, folks, so there we have it. Now again, how would we have ever been able to predict that it would all look like this off the top of our head just by looking at the function? We really wouldn't. It's a matter of nailing down a couple of points, the y-intercept, the x-intercepts, and then doing a table of values to get a couple more points, and then graphing out the rest. Or, looking at the graph to see what the rest of it looks like. Notice a couple interesting features here. On the left-hand side, the horizontal asymptote strictly comes down from infinity and levels off at 3. On the right-hand side, the asymptote comes down from infinity, drops below the horizontal asymptote, and then comes back up to meet it from down below. That's really interesting. So notice how those two horizontal asymptotes, the one on the left is coming down to 3, the one on the right comes up to 3. So that's pretty neat. And then this portion of the graph in between the two vertical asymptotes looks like an upside down parabola, but it's definitely asymmetric, and it's definitely not a parabola. It's just a curve that is squeezed between two vertical asymptotes. Yep. So folks, looking at this graph, what do you think or feel? What a weird looking graph. What is it good for? I'd say asking the question, what is it good for, is a pretty good question, because if we at least look at a graph like a parabola, if you look at the graph of a parabola, at least you could look at the parabola and say, well, sure, this is what something looks like when it falls off a building. Like if you throw something off a cliff, the parabola is going to tell you exactly how that thing falls. And so a parabola seems like a really nice function because it represents something in the real world. Whereas when you look at that function, you might say, okay, I can't really think of anything that would act like that in the real world. So what is the good of a rational function? And that's what we're going to get to today, is looking at some equations we can solve and then word problems. Well, maybe not today, maybe by Wednesday. Okay. Any questions before we move on? Anything else you want to ask? All right. Well, let's see here. So, folks, you still have a few more problems on the back, right? So 7, 8, 9, 10. Let's just do one or two of those, and specifically ones with a slant asymptote. So let's do number 7. Your number 7. All right. All right, I don't have it up here. So don't bother looking at my screen. Is there another section of this? And those are also not the same.
Our number 7 is number 6.
Yeah, okay, good. I need to update my PowerPoint. Oh, I'm so sad. All right, well, we're going to look at, don't look at my screen there. I'm just going to do number 7 with you. So everybody, we're on your page 3. We're looking at number 7. And it says f of x equals x cubed plus 2x squared plus x all over x squared minus x plus minus 2. All right. So as before, what analysis can we do right now? What are the two things we can find right now?
The y-intercept.
Yeah, we can get the y-intercept, which will be f of 0, which you'll notice if I plug 0 in for every x term, the whole numerator becomes 0, and in the bottom we just have a -2, so 0 over -2 is just 0. So the y-intercept is at 0. And then what's the other piece of information that we have? Just by looking?
It's a horizontal.
Yeah, we can do the ratio test with the horizontal asymptote. This one will be fun because it's a slant asymptote. So take a look at what happens. We take our leading terms, x cubed over x squared, which 2 of the x's top and bottom cancel out. We end up with x over 1. This right here is our slant asymptote. So when we say that the, not horizontal asymptote, but slant asymptote is y equals x. X over 1 is really 1x over x. I'm sorry, 1x over 1, or 1 over 1x. It's the line y equals mx plus b. So this is y equals mx plus b. And what that tells us is that we have a slant asymptote. I'm going to start my graph. Whose y-intercept is 0, and then the slope is up 1, right 1. So what I'm about to draw here is not the graph of the rational function, but rather the graph of the slant asymptote. So I used a dashed line, just like we have been for our vertical asymptote and our horizontal asymptote. And so what happens in this graph is that our rational function will approach that dashed line asymptotically. So there's our horizontal asymptote. I'm sorry, there's our slant asymptote. We do have a y-intercept at 0, so I'm going to make that point a little bigger. And from here, we proceed to do the rest of our analysis. So what can we factor out of the numerator? First, we factor out the x, leaving behind x squared plus 2x plus 1. Then on the bottom, we can go ahead and factor that. So what multiplies to make 2 that adds to make 1? A 2 and a 1. And now the numerator, we have to finish factoring. So I have x outside of x plus 1, all over x minus 2, x plus 1. Now, folks, I just kind of rattled that off in terms of factoring. But, you know, that's the part that might take a minute. You know, use some scratch paper and go through and say, what multiplies to make 1 that adds to make 2? That's 1 times 1. And then what multiplies to make negative 2 that adds to make negative 1? That'd be the negative 2 of the 1. So that's where we are so far. Okay, so what are the, well, first of all, can I cancel anything? Then we can cancel out that one. So there's a hole right there at x equals negative 1. The remaining factors are vertical asymptotes. We have a vertical asymptote at 2. And then the remaining pieces in the numerator are x-intercepts. So we have an x-intercept at, where's the x-intercept for this term right here? It's just x. What x-intercept is that? 1. Well, 1. 0, because really x is x minus 0. So maybe it would have been helpful to actually write in x minus 0 right there. Because that's still x, but then it reminds you that there's an x-intercept of 0, and then the other one is at negative 1. 0, and then negative 1. Oh, no. Yeah, we cannot. Thank you. Yeah, so we already know that there's a hole at negative 1, so that one's not even an x-intercept. So correct, there's only one x-intercept, and that's at 0. Now let's see, we have our vertical asymptote at 2. So 1, 2, here's our vertical asymptote. There's a hole at negative 1, so we'll just keep that in mind when we go to draw our graph. We should put a hole in it. And there was only one x-intercept at 0, which is the same as our y-intercept at 0. And otherwise, yeah, no, we don't have any other x-intercepts. Now, at this point, do we know what to draw? No. No idea. We could do a table of values. And again, if we were to do a table of values, we'd be asking ourselves, where's the graph? Right? It's kind of like the graph is invisible right now, and we want to make it appear. So you would choose some x values that would illustrate that. So for instance, I would choose at least a couple x values to the right so that I would find where those dots are. I would choose probably a value at negative 1, so I know where that point is. And then I'd skip over this one and do another one. Well, not at negative 1, that's a hole. I'd go over to negative 2. So far, the values that I would choose to make my table of values would just be a few x values that would throw in a couple more dots. Selena?
Would you use positive 1?
Oh, Selena. Yeah, positive 1. There. Yeah, so I would plug in a table of values for 4, 3, 1, and negative 2. Oh, yeah, but that one was the hole, so no, I can't plug that in. then I would have some sort of idea of what the graph looks like. I will go ahead and just graph this. And let's just find out. So this function was x cubed 2x squared is x divided by x squared minus x minus 2. There we have it. Did I do that correctly? X cubed plus 2x squared plus x all over x squared minus x minus 2. Oh, okay. Oh, okay, there we go. Well, there seems to be something where we disagree with the graph. There was definitely the x. So, I think so. Oh, how weird. This does not seem to be reporting correctly that that was a hole. Oh, there it is. Ooh, Desmos has an error in it. Look at how weird this is. Okay, so on the one hand, it's telling us that yes, there's a hole there. And on the other hand, it seems to be falsely reporting that there's an x-intercept there. So this is a genuine error on behalf of Desmos. Desmos shouldn't be showing us two different, facts. Wow, and it's so tough to get it to even recognize it. See, there's the hole. Okay, funny. I've never seen Desmos do that before. Okay, is this what we expected? I mean, does this match what our graph looks like? It does indeed. So now we can say that we have a vertical asymptote that comes up, and then it goes along that slant asymptote that way. And then it comes down. I don't have much room to show it. And follows up the slant asymptote that way. And just to make that slant asymptote more visible, we can graph it. There's our slant asymptote. And you can see that we're going up and approaching that slant asymptote as we go up to the right. And then coming back down, approaching that slant asymptote as we come back down. Now, let's finish talking about this slant asymptote idea. We actually have one more step to do. So when we do our horizontal asymptote, and it ends up that we have a higher power in the top than in the bottom, it's true that that's the slope of our slant asymptote. We do actually have to do some work. When you have a slant asymptote, so let's do that together. When you have a slant asymptote, you actually have to divide the two functions. And the only way to do that is with long division. So everybody, let's try long division out with this. You're going to do the long division of x cubed plus 2x squared plus x divided by x squared minus x minus 2. So go ahead and jot that down. It looks terrible, but these division problems are not all that bad. So recall, you look at the first term and the first term. What do you have to multiply by x squared to get x cubed? Just x, so that I put the x right there. And then what do? We multiply, so I'm going to multiply x times all that to get x cubed minus x squared minus 2x. And then we would subtract. If we were doing normal division right now, we would subtract. But instead of subtracting, we change all the signs and add. I'm going to change this from a plus to a minus, from a minus to a plus, from a minus to a plus. And then I can add, so that cancels. 2x squared and 1x squared is 3x squared. And then 1x plus 2x is 3x. And at this point, you would continue. So what do we multiply by x squared to get 3x squared? By 3. So then 3 times x squared, well, all the way across, 3 times all that. So then that'd be 3x squared minus 3x minus 6. And again, we're going to subtract, but instead we change all the signs and add. So we change this plus to a minus, minus to a plus, minus to a plus. These cancel out, and we end up with 6x plus 6. Now, when we find our slant asymptote, this is actually all we're interested in right here. That is your slant asymptote. And that's all we're interested in, is just finding the slant asymptote. So what you'll notice is that the ratio test, where you just did the ratio of the leading terms, that's just to tell you whether or not there is a slant asymptote or not. And yes, there is a slant asymptote, and it was 1/1x, but this test doesn't give you the y-intercept. So by doing the full division, you actually do get the y-intercept. And now look, when I change my slant asymptote to 1x plus 3, right, the 1x plus 3, now the slant asymptote looks normal. There we go. Now look. That looks much better. So now this red graph is coming down and approaching the slant asymptote closer and closer. And then down to the left, the red graph is approaching the blue asymptote closer and closer. And that's our final graph. So I traced this poorly. We did not yet have the slant asymptote. There. This part would be oh, because my whole slant asymptote is wrong. Oh, folks, I apologize. I need to start this graph from scratch, showing that my slant asymptote is actually at 3, not down at the origin where we had it. There we go. And then we had our vertical asymptote at 2. And now we had our y-intercept and x-intercept at 0. Now this actually looks correct. That's that part there. And of course, my graph doesn't go high enough to show that part, but I've got a little swoopy up there as well. Okay, so what did I learn from that? The ratio test is merely to tell you the existence of what the asymptote is going to look like. We had not yet finished the analysis on that slant asymptote when I drew it. We had to actually do the division first. So going forward, when we do our slant asymptote, we actually do have to do the division first, and then you would have your actual slant asymptote. So definitely let's try one of those right now. Let's do one more slant asymptote, and then we'll move on. All right. So the one we had just done was number 7. Okay, there's then we'll do number 8. Let's do number 8. And then you can all cross out 9 and 10. So we'll just finish up number 8. So number 8, we have our function. Over okay, so what information can we see just by looking? We have our y-intercept, which is f of 0, which is just 1/1, which is 1. So our y-intercept is at 1. And the ratio of leading terms is x cubed over x squared. And since the power in the top is larger than the power at the bottom, we are going to end up with a slant asymptote. What we don't know yet is the actual equation of the slant asymptote. So now we would go ahead and do long division. So we would divide our x squared plus 1 into x cubed. And you know what, folks? Put in a 0x squared minus 3x plus 1. Whenever you do synthetic division or long division, it's helpful to have that additional term in there so you can see it. All right, so same question. What do you multiply by x squared to get x cubed? You multiply by x. And then multiplying, I'd have x cubed. And then x times 1 is just 1x. So I put a 0x squared term and then 1x. And then we subtract or change the signs. And then cancel. That's still 0x squared. We don't even have to write it down. And negative 3x minus 1x is negative 4x. Then you drop down your next term.
So now in this case, we're done already because there's nothing we can multiply by x squared to get negative 4x. So that's as far as the analysis went, and that is our slant asymptote. What's that? Well, that's 1x plus 0, like mx plus b. So the y-intercept is 0. So the slant asymptote has a y-intercept of 0 and a slope of 1 over 1. So there's our slant asymptote. And we also know that we have a y-intercept of 1. I'm going to draw that in there. That's all we know so far. No, I didn't do it yet. But over here, where we're talking about how to understand an entire rational function, right here under horizontal asymptote, I'm going to remind us all that if the power is smaller on top, so if the top power is smaller, then your horizontal asymptote is at y equals 0. If your powers are the same, ax squared over bx squared, then the horizontal ratio, or the horizontal asymptote is at a over b, the ratio of the leading coefficients. And if the coefficient on top, or if the power of x on top is larger than the power on bottom, then that's when you have a slant asymptote. So if the exponent is larger on top, it's a slant asymptote. If it's smaller on top, the slant or the horizontal asymptote is just 0. And if the powers are the same on top and bottom, the horizontal asymptote is just the ratio of those two coefficients. I think we've seen one of all of those now. Okay, so let's finish number 8. The rest of our analysis would be to factor. Maybe you all already factored it. How do we factor the top? Ooh. X cubed minus 3x plus 1. Then on the bottom, we have x squared plus 1. This is challenging. First of all, look at the denominator because it's a little easier. How do you factor x squared plus 1? You don't, because this is an x squared minus 1. If it was x squared minus 1, it'd be the difference of two squares, and you could factor it. But this is x squared plus 1, so you can't factor it. So we'll write that. Can't factor it. Furthermore, x squared plus 1, if you were to wonder, where are those x-intercepts? Does x squared plus 1 even have x-intercepts? X squared plus 1 is a parabola that looks like this. Does it have any x-intercepts? No. So the bottom can't be factored. It cannot be factored like this with real numbers, only imaginary numbers. And therefore, is there a vertical asymptote? There is no vertical asymptote either. Because the denominator will never be 0. X squared plus 1 will never be 0. And therefore, the denominator will never be 0. Which means you won't have a vertical asymptote and you won't have a hole. Because the denominator will never be 0. Okay, so what about the top? How do you factor x cubed minus 3x plus 1? Yeah, we would have to fall back on synthetic division. We'd have to fall back on everything that we did in chapter 3. Fortunately, you can also just graph only the numerator, so x cubed minus 3x plus 1. And by graphing, you can just look and see what your x-intercepts are. So one of them is at negative 1.879, and then 0.347, and whoa. Is that really the function? X cubed minus 3x plus 1? Well, those are very unfortunate. All three of those x-intercepts are decimals, which means they're all irrational. So we won't be able to factor that using rational roots theorem either. There are no whole number, and it does not appear to be any fractional. No, one of them has to be a fraction. Boy, that's such an unfortunate problem. Yeah, I don't see a way to factor that either, folks. That is, without using square roots. Is that really x cubed minus 3x plus 1? Sure is. And yet, Well, I tell you what, this problem goes a little beyond what I'm going to expect of you on the test. I apologize. We can go ahead and just take a look at what our graph is by taking a look on the graphic calculator. But it looks like this one also does not factor as whole numbers. So let's just take a look and see what our graph would actually look like. So we've got that divided by, is it x squared plus 1? All right. Well, that is really cute. Now what you'll notice is that we have the same x-intercepts on this graph as we did with the polynomial that we were looking at. They're all those same decimals. And the difference is that, sure enough, we don't have any holes, we don't have any vertical asymptotes, but we still do have the slant asymptote. And the slant asymptote was at 1x plus 1? No, 1x plus 0? Yeah, sure enough, that's what we have here. So the purple line is just showing you where the slant asymptote is. And if you head up, you can tell that the green line is getting closer and closer to the purple line. And as you head down this way, the green line is getting closer and closer to the purple line. And so what can we conclude? We can conclude that the x-intercepts are the same as the x-intercepts as the polynomial, which we did not end up factoring with synthetic division. We just looked at the graph to know where those points were. And then you would sketch out your graph. So let's see. We had x-intercepts at negative 1.8 right there, and an x-intercept at 0.347, which is about there, and an x-intercept at 1.5, which is about here. And then looking at our graph, it went up, down, and up. And at that point, you'd think, well, gosh, that looks just like a normal polynomial, except for the fact that our tails leave asymptotically. And yeah, love it. All right. So other than the fact that it wasn't, we didn't actually solve for the x-intercepts in the numerator, we just got them from the graph. This is a pretty interesting graph because it takes our polynomial that you can tell it looks like a polynomial, except for the fact that our tails shoot off asymptotically rather than just the normal way tails go from a polynomial. Okay, and I believe that's it. So everybody, you crossed out 9 and 10? All right. Now, in section 4.2, it's more graphing problems, which, of course, I have all my numbers wrong. But we've already done quite a few graphing problems. I don't feel like we need to do any more of these together, because we've now done quite a few graphs. So let's just do, yep, in fact, oh, that's where I think I got some of these problems from. I think I mixed them around. I'm sorry, folks, that's very confusing. I have to fix my PowerPoint. I think we're done for now. I think we're done with these graphing problems for now. Let's take a break on graphing. I'll go back through the online more homework and see if there's any more types of graphs that we should do together. Otherwise, let's move on forward to section 4.3. Okay, you know what we're going to do? We're going to take a break. Because I need to fix my PowerPoints. None of these problems are matching up. I'm very confused. Apparently, the document that I printed out for you folks is an updated version of the document I had. So let's take our break. It's 9 o'clock. It's almost 9 o'clock anyway. So it's 8:57. Let's all come back together at 9:07. And my PowerPoint will be fixed and we'll be able to move forward.
Yeah.
Okay.
folks, let's get back together here. We're going to start on section 4.3. My slide shows what you have, so we're all looking at the same thing here. So up until this point, we've been looking at rational functions and asking the question, how do we graph it? Like, how do we get the information out of the function itself to know what the graph would look like, and then knowing what the graph looks like, how do we figure out what the function should look like? Whereas now, we're going to just look at some standard equations. These are just normal equations where you have an equal sign, and you're wondering, what number do I plug in for x such that the equation would become true? So let's start by writing that question down together at the top of what you're asking. And the main question we're asking is, what numbers can I plug in for x to make the equation true? Notice I'm purposely asking the question this way instead of just saying solve for x. Because if you just dive in and start solving for x, you might end up getting a number that, when you plug it in, actually does not make the equation true. And that could happen because, specifically, we have denominators in all of these equations. And because we have denominators, we have at least maybe one value for x that if you plug it into this equation, it'll actually make the bottom equal to 0, which makes the whole fraction undefined, which makes the whole equation not true. So the first thing we want to do is just take a look at the denominator and say, what value can't I plug into the equation? So we're asking what numbers can I plug in for x to make the equation true, but we also need to ask the question, what numbers can't I plug into this equation because it would make it undefined? So it's really two questions we're asking. What number can I plug in to make the equation true, and what number can I plug in to make the equation undefined? So let's start with number 1 and ask the second question first. What number are you not allowed to plug in? You are allowed to plug in 0. What number am I not allowed to plug in right here? You'd have to look at the denominator. Oh, and maybe that's why you said 0, Josh. You don't want the denominator to be 0. So because we don't want the denominator to be 0, let's go ahead and say 5x plus 4 had better not equal 0. We're really just doing a domain question. We're really just saying, what's the domain? The domain is any number except for what you plug in to make the bottom equal 0. So now we know 5x better not equal -4, and x better not equal -4/5. So what we found so far is the number we cannot plug in to this equation. Because otherwise, the whole thing would be -4/5 divided by 0, which is undefined. And undefined certainly does not equal 3. Okay, so now let's proceed with solving the equation. Now that we know right up front that our answer better not be -4/5, let's proceed to solve this equation. How would you solve an equation like this? I feel like maybe we already talked about how do you get x out of the denominator in general? If you have x in the denominator, how do you get it out of the denominator? There's two different strategies we could take with this equation. How can we solve for x? We've got an x in the top and the bottom. That makes it a little tricky. What can we do? Multiply by the reciprocal. Oh, you mean on both sides? That's a really interesting idea, Josh. I'm going to write it down over here. If we had, what is this? X over 5x plus 4 equals 3. If I did multiply both sides by the reciprocal, I don't even know, is this what you mean? Multiply both sides by the reciprocal? Yeah. It's an interesting, fun idea because, sure, it would cancel it out over here and we just have 1. But now over here, we'd have 3 5x plus 4 all over x, and we still now have the other x in the denominator. No, but it was a great idea. I really liked it. So what can we do instead of multiplying by the entire reciprocal? Just multiply by the denominator. That would be correct. Anytime you have an x in the denominator, you want to multiply by whatever is in the denominator. So let's go ahead and multiply both sides times 5x plus 4. And why is that helpful, to multiply both sides times the denominator? What happens over here on the left? Now that cancels itself out, and now we just have x equals 3 5x plus 4. So the general strategy is multiply both sides by the denominator. That is the denominator that has the offending x. So now what do we have? We have x equals, distribute to 3, 15x plus 12. And you can go ahead and move all the x terms. Now, whenever you do something like this, you're going to end up with x terms on the right and on the left. Where do we want all of our x terms? We typically bring all the x terms to the left and bring all the number terms to the right. So I'll go ahead and bring my 15x over to this side. Now that we have negative 14x equals 12. And then we divide both sides by negative 14. We get x equals negative 12/14, which simplifies to negative 6/7. Is x allowed to be negative 6/7? Yeah, x is allowed to be anything except for negative 4/5. And so we are certainly allowed to plug negative 6/7 into this equation. And if we do, apparently what will it equal? Apparently it'll equal 3. Have we checked that yet? We haven't checked it. I want you to know it's fairly easy to check on your graphing calculator. You can plug negative 6/7 into this structure. It's going to be negative 6/7 over 5 times negative 6/7 plus 4. And folks, you can plug that whole thing into your calculator. And I encourage we all go ahead and try that. Go ahead and try plugging that whole thing into your calculator. You need as many parentheses as I have up there. So you would take your calculator, and I tell you what, I'm going to write it out sideways for what you would see on your own calculator to verify that our answer actually is correct. In your own calculator, you would type in parenthesis negative 6 divided by 7 parenthesis divide by parenthesis 5 parenthesis negative 6 divided by 7 parenthesis plus 4 parenthesis. Now that's a tall order. Just looking at that, are you like, that's going to equal 3? Probably not. Well, let's find out. Negative 6/7 divided by parenthesis 5 parenthesis 6 7 4. And what does it equal? It does in fact equal 3. So notice what we accomplished. It says solve. And sure enough, we did. X equals negative 6/7. And we now have 2 statements that we know. So for number 1, you would say if x equals negative 6/7, the equation is true. If x equals negative 4/5, the equation is undefined. And if x is anything else, the equation is false. That's a nice little summarizing statement there at the end. We're saying, hey, here's an equation, x over 5x plus 4 equals 3. And out of all the numbers in the universe that you can possibly plug in for x, there's only one number in the universe that will make that equation true. That was the negative 6/7. There's one number in the universe you can plug in, and the whole thing would become undefined. And then any other number that you can possibly imagine, like the number 10 or the number negative 50. Plug anything else in, and that whole equation will just become false. And that's interesting because any given equation has kind of a 3-way life. There's certain numbers that you can plug into the equation that would make it true, certain numbers you can plug in maybe to make it undefined, and certain other numbers you can plug in and make it false. Okay, let's try number 2 together. We're going to try the exact same approach. So here's number 2. And so we have our 3x minus 1 over x squared plus 1 equals 1. And the very first question, again, that you'd like to ask is, when will it be undefined? Because you'd like to know right up front what numbers you can't plug in for x. So how do we know what number you can't plug in for x?
X squared plus 1 can't 0.
Right. X squared plus 1 had better not equal 0. Because then the denominator would be 0 and it'd be undefined. And what we find out there is, that tells us that x squared had better not equal -1, or x had better not equal I, which, that's fine. Because we're only ever interested in what real numbers can we plug in. So in other words, can I plug any number I want into this equation? Yeah, I can plug any number I want into this equation. There's no restrictions. The domain is all real numbers. Okay, so now we proceed to solve. Now, again, whenever you have a denominator, you can always just multiply that denominator on both sides. But I want to show you one other way of doing it, folks. Instead of multiplying both sides by x squared plus 1, what's one other thing you could do? And I'll suggest it by rewriting 1 as 1 over 1. How could you solve this equation? Do what? The idea that we already know will work is just to multiply x squared plus 1 on both sides, because that will cancel it from here. But what's the other thing that we can do to solve an equation that has a fraction equaling a fraction? Starts with and ends with cross multiplying. Cross multiplying. So let's try cross multiplying, folks, because both of these solutions are good. So you can either just multiply the x squared plus 1 over the other side, or instead, I'm going to cross multiply the denominator on the right up to the numerator on the left. So that's 1 times 3x minus 1. And then I'm going to multiply the x squared plus 1 up to the 1 on top. So that's 1 times x squared plus 1. And that's cross multiplying. Cross multiplying achieves the same goal. It just goes by a different name. And cross multiplying would be handy if, say, we had variables in all 4 spots. Then by cross multiplying, you get rid of the fractions, and we end up with 3x minus 1 equals x squared plus 1. And we've essentially gotten rid of the denominator. In fact, that'd be a good thing to say right up front about the whole rest of the unit that we're working on. The way to solve rational equations is to get rid of the denominator. That's always our goal. If you want to solve an equation with a denominator, get rid of the denominator. Okay, so now what? We have 3x minus 1 equals x squared plus 1. What do we do? Yeah, and because there's an x squared term, we want to bring all the terms to the left. We want to bring all of our terms to the left, or all the terms to the right. Since x squared is already on the right, I'm going to go ahead and move my 3x over to the right, and I'll move my 1 over to the right. And that way I have x squared minus 3x plus 2 equals 0. And what we have now is just a quadratic. So when you have a quadratic, we want all the terms on one side equaling 0. Whereas when we were just solving for x without a quadratic, then it made sense to put all of your x's to one side and all of your numbers to the other side. Okay, can we factor this? We'll multiply to make 2, that has to make 3. Yeah, x minus 2 times x minus 1. And so by the zero product rule, which is why we want all the terms to one side equaling 0 so that you can do the zero product rule, we get x equals 2 and 1. So let's put all that together. We were given an equation, and they told us solve it. That means find the numbers you can plug in to make it true. So apparently, if I plug in 2, this equation will be true. If I plug in 1, this equation will be true. Whereas if I plugged in I or negative I, this equation would be undefined. But we're not talking about plugging in imaginary numbers anyway. The key is you can plug in any real number. There's no domain exclusion. And specifically, plug in 2 or 1, then the equation will be true. Now, should we go ahead and check? When you're done solving, should you go ahead and check? Yeah, definitely. Plug in 2, plug in 1. And something like this you can more or less do in your head. So 3 times 2 is 6 minus 1 is 5. Over 2 squared is 4 plus 1 is 5. That's 1. And then if I plug in 1, 3 times 1 is 3 minus 1 is 2. Over 1 squared is 1 plus 1 is 2. Yeah, both of those are equal to 1. All right. Questions about what we've done so far?
You're either multiplying both sides by the denominator, or you can cross multiply. All right, everyone looking at number 3? Number 3 is a little bit more in line with what we'd expect. Denominators everywhere. We have lots and lots of denominators. So what can we do here? Number 3, everyone write it down in your own handwriting real quick, especially because I want you to put the x plus 3 in parentheses and put the x minus 3 in parentheses. And then what should we immediately do with the x squared minus 9? Over on the right-hand side, when you see x squared minus 9, what should we immediately do? We want to rewrite that as x plus 3x minus 3. So this is the equation we all have. Now, I'd like us to continue with the practice of noting first your domain exclusions. What numbers can't I plug in for x? Yeah, do we all agree that 3 and negative 3 are domain exclusions? You can pretty much just write that down. You know, you could set each of those equal to 0, but I think we all know the answer is 3 and negative 3 that x can't be. Okay, so there's a couple different ways that you can approach this problem. The main way is to look for the common denominator and multiply through all the way across by the common denominator. Now, we need to say a couple things about that. Let's look at a normal example with some numbers. Let's say that I had 1/3 plus 1/5 equal 1/5. Well, sorry, I'll put an x in there somewhere. There. Let's say we had 1/3 plus 1/5 equals a 15, which I can immediately see that that 15 I could actually write as 3 times 5. So first of all, what's the common denominator? 15, right? In this case, that's pretty simple to see that it's 15 because we're dealing with numbers and you can think, well, yeah, 3, 5, and 15 will go into 15. So 15 is our common denominator. I'd like to suggest a different way of looking at this, and that is asking, what would each denominator need to have so that every denominator would be the same? So for instance, this denominator already has a 3, this denominator already has a 5, and this denominator has both a 3 and a 5. And what I'd like to suggest to you is that each denominator is essentially like a selfish child, and whatever toy one denominator sees that the other denominator has, it also wants that toy. So like this child has a 3, but he sees that kid has a 3 and a 5, so he's like, hey, I want a 5 as well. And this kid only has a 5, and he sees that kid has a 3 and a 5, so he wants a 3 as well. And then at that point, if they each had a 3 and a 5, then as selfish children, they would all have the same toys. And we'd have a common denominator. So what does this denominator want to have? Yeah, this denominator wants a 5, this denominator wants a 3, and this denominator doesn't need anything because it already has a 3 and a 5. So the way we would do that then is we'd say this denominator needs a 5, so I'm going to multiply top and bottom by 5. And then this denominator needs a 3, so I'd multiply top and bottom by 3. And then this denominator already has it. And so from here then I can say that this is really 5/15, and this is 3/15. And then that equals x/15. And now that they all have the same denominator, what do you know must be true about the numerators? Yeah, so this one we know 5 plus 3 must equal x. All right? So that's just a basic example using regular numbers instead of variables to see how you could create a common denominator. And furthermore, that once you do have a common denominator, you can just add the numerators together and do that equation. But just to make it, to show you the last step that they're going to do, that is, if you multiply the entire equation by the common denominator, so I'm going to multiply this entire equation by the common denominator, what happens to all the 15s? It would cancel out. Now watch, I'm going to do it. I'm going to write down on the top here, so that'd be 15 times 5 over 15. And then that'd be 15 times 3 over 15. I'm distributing all the way across, and then 15 times x over 15. And what happens to all of the 15s? They all cancel out, and you'll notice, what are we left with? just the numerators. We're left with just the numerators, and this is a valid operation because we multiplied through by the common denominator. So when you have an equation with fractions, the first thing you want to do is find the common denominator, and then if you multiply through by the common denominator, it cancels all the fractions and you're just left with numerators. And that's really what we want to do. So looking again at this big long equation that we have here, our goal would be, how can we cancel all the denominators? What would I need to multiply by that would cancel all the denominators? And in this case, this child has an x plus 3, this child has an x minus 3, and this child has both an x plus 3 and an x minus 3. So what would this fraction still need? It would need an x minus 3 top and bottom. And then this denominator would still need an x plus 3 top and bottom. Whereas this denominator is already complete. Okay, so what we'll do then, because ultimately what we really want to do is cancel all of these denominators, we now know that our common denominator, and I'm going to write it down, our common denominator is x plus 3, x minus 3. If we did go ahead and give all of these fractions a denominator of x plus 3, x minus 3, there would be a common denominator. So I just noted that our common denominator is that. And what we'll do now is multiply all the way across by that common denominator. So I'm going to distribute that all the way across to all three of them. I'm going to write it out so you can actually see what cancels and what doesn't. So if I now distribute that term, the common denominator, to all three numerators, my first numerator is going to be 1 times x plus 3, x minus 3, all over x plus 3. And then my second fraction would become 1 times x plus 3, x minus 3, all over x minus 3. And then on the other side of the equation sign, I'll have x squared minus 3 times x plus 3, x minus 3, all over x plus 3. Now you might look at that and say, we just made things worse. Because it certainly is a lot more busy. We found the common denominator, we multiplied everything by the common denominator. But now what's the benefit of multiplying everything by the common denominator? Yeah, everything all the denominators cancel. We no longer have any denominators, which is wonderful. The denominators are what made this problem tricky looking in the first place. Our goal is to get rid of all the denominators. So now I just have 1 x minus 3 plus 1 x plus 3 equals x squared minus 3. So we effectively just got rid of all of the denominators. And this technique is called multiply through by the common denominator. So you distribute your 1s. We have 1x minus 3 plus 1x plus 3 equals x squared minus 3. What can we do over on the left? We can condense quite a bit. 1x plus 1x is 2x, and then the negative 3 and the positive 3 cancel out. So we have 2x equals x squared minus 3. And we do want to put all of our terms together. I'm going to move, since my x squared is already positive on the right, I'll leave that there and I'll just move the 2x over. So now we have 0 equals x squared minus 2x minus 3. And what can we do with that? Yeah, we can factor that. And so that would become, is it x minus 3, x plus 1? And so our two solutions are x equals 3 and x equals negative 1. Now notice what we think we just found. What we think we just found is that if I plug 3 or negative 1 into that original equation, it should be true. So let's look at that. The original equation was 1 over x plus 3 plus 1 over x minus 3 equals
equals x squared minus 3 over x squared minus 9. So before I go plugging 3 and negative 1 in, let's just remember right up front, what were the two numbers I said I could not plug in? Yeah, 3 and negative 3. So in fact, I already know that this is not actually a valid answer. This is very surprising because algebra led us to the result that x is 3. But our previous analysis told us that x couldn't equal 3. So what I'm going to do now is circle this answer and put a big cross through it and call that answer extraneous. Extraneous. Extraneous has a particular math definition which states that this solution, even though algebra told us that solution works, that is not actually an answer to the equation because it's a domain exclusion. So even though the algebra led us to the number x equals 3, we know it's a domain exclusion, so it doesn't actually work. So our only actual answer then is negative 1. And if I plug in negative 1, that gives me 1 over negative 1 plus 3 is 2, plus 1 over negative 1 minus 3 is negative 4. And then negative 1 squared is 1 minus 3 is negative 2, and negative 1 squared is 1 minus 9 is negative 8. And that gives me a half minus a fourth should be equal to a fourth. And indeed, a half is really 2/4 minus 1/4, and 2/4 minus a fourth is a fourth equals a fourth. So yes, x equals negative 1 is a solution because when I plug it into the equation, it does make the equation true with 1/4 equals a fourth. And you might say, do I have to do that part? And I would say, yeah, that's a really good idea to do that part to actually check to make sure that your solution works. What would have happened if I plugged in 3? Yeah, let's try plugging in 3. That'd be 1 over 3 plus 3 is 6. And then 1 over 3 minus 3 is 0. Oh, 1 over 0. And then 3 squared is 9 minus 3 is 6. And 3 squared is 9 minus 9 is 0. Well, this has all sorts of problems. Well, 2 problems. Both of those denominators are undefined, and therefore the whole equation is undefined. So again, x can't equal 3. Okay. Well, folks, this was a really good problem because it demonstrates what you're trying to do. What you're trying to do is find the numbers that you can plug in to make the equation true, but you need to be mindful of the fact that there are numbers that you're not allowed to plug in because they could make it undefined. And so whenever you're done solving for numbers that you think you can plug in to make it true, you have to double check it against the numbers you know it can't be because it would make the fraction undefined. One more thing, just to point out, just in case you like this way better. We started with the problem 1 over x plus 3 plus 1 over x minus 3 equals x squared minus 3 over x squared minus 9. Consider, if we wanted to, you could have just given a common denominator all the way across. So we could have made this 1 over x plus 3, and then 1 over x minus 3. And over here, x squared minus 3 over x plus 3, x minus 3. And again, folks, what does this denominator want to have with it? We want to have an x minus 3 right there. So I'm going to put it in, x minus 3 top and bottom. Why am I allowed to just multiply x minus 3 on top and bottom? Right, we want this denominator to be that denominator, but why am I allowed to just multiply the same thing on top and bottom? Like, let's say that I had the number 5, which is really 5 over 1. Am I allowed to just multiply top and bottom by 10 if I want to? Is that valid to just multiply the same thing on top and bottom? Yeah, why is it valid? What's 10 over 10? 1. So multiplying times 10 over 10 is really just multiplying by 1. And multiplying by 1 doesn't change anything. So we can rewrite it as 50 over 10, but that still simplifies back down to 5 of them. So anytime you want to, you can multiply a fraction by the same thing on top and bottom, and that's a valid move. Okay, so going back to here, I multiply top and bottom by x minus 3. Here, what do I need? I need an x plus 3. And now you'll notice I have the same denominator all the way across. And again, if you have the same denominator all the way across, you can just focus on the numerator. So now I can say 1 times x minus 3 plus 1 times x plus 3 is x squared minus 3. And is that the same equation we ended up solving? Yeah. So did anyone like this way better? Just curious if you did or not. If you did, that's perfectly fine. You can do that. You could just go ahead and create a common denominator and then just focus on solving the numerator. And that will give you the same results as what we just did. Either way, you still need to do your domain analysis of noting what numbers you cannot plug into the denominator. But maybe you like this way better than multiplying all the way across by the common denominator. We're going to try multiplying through by the common denominator at least one more time, just so we can see how the procedure works. Okay, so what was that? That was number 3. Let's try number 4. Number 4. Oh, no, it's not exactly the same. Let's go ahead and do number 4. Okay, before we start, let's clarify, what are some of our goals? We want to solve for x. We want to find what numbers to plug in for x that make it true. And we want to find what numbers to plug in for x that make it undefined. And what's our larger manipulative goal? We want to do what to that x plus 1 in the denominator? What do we want to do to all denominators? Get rid of them. Yeah, we want to get rid of the denominators so that we just have a normal standard polynomial to solve. So that's quite a few goals. We want to find out what number to plug in for x to make it true, what number to plug in for x to make it undefined, and we want to get rid of the denominator so we can just solve with normal algebra. So everybody, we can go ahead and say our domain exclusion. What can't x equal? Yeah, x can't equal -1 because then the denominator would be 0. All right. Well, it's your choice. You can either multiply both sides times x plus 1, or you can cross multiply. Either way, you would. I'm going to go ahead and multiply both sides times x plus 1. So that cancels out. We have 2x plus 17 equals x plus 5, x plus 1. Folks, someone might be tempted right now to set each of these parentheses equal to 0 and say x equals -5, x equals -1, and x equals -17/2. Why is that not correct? Exactly right. You can't just set parentheses equal to 0 anytime you want. It has to only be when the whole equation equals 0. So we can't actually do the 0 product rule yet. Well, what do we have to do instead? What was your second option? Oh, you mean move these over?
Yeah.
Right, well, we have to end up doing both. So let's go ahead and FOIL that. So we have 2x plus 17 equals x squared plus 1x plus 5x plus 5. And that gives us x squared plus 6x plus 5. And again, when we have a quadratic, we want all the terms on one side. So we want to set the whole thing equal to 0. So I'll go ahead and move my 2x over, and then move my 17 over. And now I have 0 equals x squared plus 4x minus 12. Folks, I want you to notice what we just accomplished. We started with an equation that had a denominator. And our whole goal was to get rid of that denominator and rewrite it as a normal equation. And that's what we just accomplished. So you notice we haven't even solved for x yet. But what we did was we manipulated this equation into a new equation that we actually know how to solve. So now we can factor this. What multiplies to make 12 that adds to make 4? Yeah, x plus 6, x minus 2. And so now we can say x equals either x equals -6 or x equals 2. And is x allowed to be -6 or 2?
Yes.
Yeah. Yeah, the only thing that x can't be is -1.
So now to like report our final answer, we know the domain is anything except -1. And the solutions are x equals -6 and 2. Now, to be fair, we can immediately just look and say, well, good, we didn't solve for -1, so that's fine. But should we still check our work? We should still plug our numbers in. And for the most part, it doesn't take that long to plug our numbers in. I'm just going to go ahead and write down 2x plus 17 over x plus 1 equals x plus 5. And just by a quick spot check, we should be able to check. So if I plug in -6, 2 times -6 is -12, plus 17 is 5. And then -6 plus 1 is -5. And then the other side of the equation, -6 plus 5 is -1. And sure enough, -1 equals -1. So our first solution of -6 is true. Now I'll plug in 2. 2 times 2 is 4. 4 plus 17 is 21. Over 2 plus 1 is 3. And over here, 2 plus 5 is 7. And sure enough, 21 divided by 3 is 7 equals 7. That's also true. So you do want to finish your analysis by actually plugging in the numbers and checking to see that it really does make the equations true. All right. We have a couple more minutes to go and a couple more problems that we can try. When does class end?
10.
Oh, 10, 20. Oh, we still have lots of time. Okay, good. Let's do it. I'm going to come back over here now. All right. And number 5, folks, I want to throw in one more idea with you, and that is notice that the thing on the left could be considered a function. And what are we asking about this function? Yeah, what we're really saying is what input would I need to plug into this function so that the output was 1? So what's my input that'll make an output of 1? And so let's consider then what else we're saying about this. We have some sort of rational expression. There's a graph, and we're wondering when does that graph have a y value of 1? So let's just look real quick. I want you to see that you can actually solve any equation by graphing it. So take a look. It's really exciting. Here's my graph, x squared minus 2x plus 1 divided by x cubed plus x squared minus 2x. Okay, so there's our rational expression. And we're wondering, when does that equal 1? That is the y value of 1. So I can go ahead and graph the horizontal line, y equals 1. And folks, when does that graph equal 1? Did I copy that down correctly? X squared minus 2x plus 1, x cubed plus x squared minus... Did I copy it down correctly? So when does my green graph touch the black graph? Does it? It looks like it doesn't. My oh my, what does that imply about the solution for x? Yeah, that there is no solution for x, right? Because we're looking at this expression over here as a function, and we're asking when will that function have an output of 1, meaning a y value of 1. And just looking at the graph real quick, it doesn't look like there ever will be. So will the left-hand side ever equal the right-hand side? No. And we know that by graphing it. But let's go ahead and see where the algebra leads us. What's the first thing we want to check? What are our domain exclusions? So everybody, for our domain exclusion, we're wondering, this thing had better not equal 0. So for the domain, you would say x cubed plus x squared minus 2x had better not equal 0. And then how do we solve that? What do we factor out? We can take out an x, so now that's x squared plus 1x minus 2. That better not equal 0. And then can we factor the quadratic?
Yes.
Yeah, 1 multiplies to make 2, that adds to make 1. So that'll give us x plus 2, x minus 1. That better not equal 0.
So what does that tell us then? Right. That was quite a domain exclusion list. So what we now know is that this equation, you cannot plug in an input of 0, -2, or 1. What were the features on the graph? Let's look at 0, -2, and -1. Where's x equals 0? What's happening at x equals 0? What do we have? Right, because what is this feature called right here? We have a vertical asymptote. What about at -2? What do we have at -2? Another vertical asymptote. And then what about at 1? Oh boy. Yeah, it's supposed to be a hole. What the heck? Oh, there it is. Boy, Desmo sure is funny like this. It's not coming right out and telling us when there's a hole. You really have to trace very carefully along it. All right, so there was our hole. So if you want to now, go ahead and write that down on your 3 parts, the 3 things that you're not allowed to let x equal. X couldn't equal 0 because it was a vertical asymptote. It couldn't equal -2 because it was a vertical asymptote. Couldn't equal 1 because it was a hole. Okay, so we already know the answer. We already know that this equation will never be true. There's no number that we can plug in to make it true. Well, let's finish solving it anyway. We want to transform this equation so there's no denominator. So how do I get rid of the denominator? Here, we multiply it off to the other side. So we start with x squared minus 2x plus 1 being divided by x cubed plus x squared minus 2x equals 1. So we're going to go ahead and multiply both sides by the denominator. So over on the left, that just all cancels out. And on the right-hand side, we have x cubed plus x squared minus 2x. And so now what we have is x squared minus 2x plus 1 equals x cubed plus 1x squared minus 2x. Well, now what? Yeah, we want to move all the terms to the right. Well, I mean, wherever my x cubed term is. Since my x cubed term is already positive on the right, I'm going to move all my terms to the right. Well, look, before I start moving things, what do you notice?
2x minus 2x and x squared cancel each other.
Yeah, anything you have on both the right and the left, you can cancel out. I have a -2x on both sides. I don't know, 1x squared on both sides. So what I really now have is just 1 equals x cubed. And this now is just a normal equation I can finish solving. X is being cubed, so you cube root both sides. And what is the cube root of 1? Yeah. Now, folks, what if you didn't know that? What's the cube root of 1? What does that even mean? What number times itself 3 times equals 1? So definitely the answer is 1. How can you type it into your calculator? You folks know that you have a cube root button on your calculator? If you go into your calculator and hit the math button, under math, there's, on my calculator, it's the 4th option down. It says cube root. So that's one option for you, is that you can hit your cube root button. What's the other option? How do you do the cube root of any number? That's the same as taking that number x to the power of 1/3. So folks, either of those calculator options will work for you. So you can either do the cube root button on your calculator, or you can take that number and raise it to the power of 1/3. Likewise, if you had the 4th root of x, or the 4th root of some number, you can calculate that by doing x to the power of 1/4. It might have been a while since you've done something like that, so I just want to remind you all. So either, like for instance, your calculator does not have a 4th root button. So you would have to know, you take that number and raise it to the 1/4. Okay, so in any case, the answer is 1. So what does that mean?
We just found out that there's only one number we can plug into this equation to make it true, x equals 1. But are we allowed to plug in x equals 1? No, because there's a hole. So what that tells us then is that there is no solution. And you would take the one solution that you got, x equals 1, cross it out, and call it extraneous. The one solution that your equation gave you was extraneous because it was a domain exclusion. Okay, one more problem. Try number 6. We have negative x cubed plus 4x all over x squared minus 9, and that equals 4x. Now again, the graphical interpretation. I want you to notice that what you have on the left could be considered a function, and what you have on the right is considered a function. And so you could go into something like Desmos, and you could plug in the first function. So that would be negative x cubed plus 4x divided by x squared minus 9. So there's one function. There it is. Wow. That's a fun one. So that's one particular graph. And then they're saying, when does that equal the function 4x? And so I graph 4x. And so now what are we asking? We're saying, when does the red function equal the blue function? So graphically, where are those points where the red function equals the blue function? Those points. We're looking for the intersection points. We're saying, when does the left-hand side of the equation, which is a graph in and of itself, the red graph, when does it equal the right-hand side of the equation, the 4x, which is a graph in and of itself? And we're saying, when do those points intersect each other? So everybody, go ahead, let's write down our answers. When will number 6 be true? When x equals 0, 2.828, or negative 2.828? So I'm going to go ahead and write down my answers right now. That equation will be true when x equals plus or minus 2.828 and 0. And I'm just kind of making a note to myself. I'm saying, hey, I already looked up the answer. I already know what the solutions to that equation are going to be. And now I have this as a guide so that as I proceed to do the work, I can check myself and make sure I didn't make any algebra mistakes. Okay, so what are we going to do? What do we do first? What did you say?
X squared minus 9 cannot.
Right, let's go ahead and check our domain exclusion real quick so we know what we can't let x equal. So we know that x squared minus 9 had better not equal 0, which means x squared had better not equal 9, which means x had better not equal plus or minus 3. So we know those are our domain exclusions right up front. And in fact, what was plus or minus 3 on the graph? Was that our vertical asymptotes? Yeah. There we go. Yeah, the plus or minus 3 were the two asymptotes that we saw on the red graph. So that's our domain exclusion. Those were two asymptotes. What's that? Yes, that also would have been the difference of squares. So x squared minus 9. Very good, Josh. So with x squared minus 9, if we're saying that can't equal 0, then x plus 3, x minus 3 can't equal 0, which means x can't equal 3 or negative 3. Is that what you're thinking, Josh? Yeah. Yeah, both of those ways work. Those are perfectly good for finding the domain. Okay, now what? How do we get rid of the x squared minus 9? Then we're going to multiply both sides times x squared minus 9. And that way it cancels it on the left. We have negative x cubed plus 4x equals, and now we distribute, so 4x times x squared and 4x times negative 9, so that's 4x cubed minus 36x. Our goal is to get everything on one side. And I already have a positive 4x cubed term on the right, so I'm going to go ahead and move everything to the right. So plus my x cubed, and then minus the 4x. And now I have 0 equals 5x cubed minus 40x. Why do we put all the terms on one side again? Why is that our general algebraic strategy, to always put all terms on one side? What, Jenny? Yeah, so the whole thing equals 0 so that we can use the zero product rule. Because now I can just factor out a 5, and I can factor out an x. So I have 5x outside of x squared minus 8 equals 0. And so now we have a zero product rule. And I know that either 5x will equal 0, or x squared minus 8 will equal 0. In the first case, that's just x equals 0. And that was one of our solutions, x equals 0. And then in the other case, we move the 8 over, and we get x squared equals 8. And when you square root both sides, you get x equals plus or minus the square root of 8, which is 2.828. Is that correct? I think so. Yeah, 2.828. So you'll notice the algebra bore out what we saw in the graph. In our graph, we knew that this graph intersected this graph at plus or minus 2.828 and 0. And when we finished doing the algebra, we got x equals 0 and plus or minus 2.828. Are any of those solutions our domain exclusions? No. So we really do have 3 solutions. Notice, folks, if you were to kind of write like a nice summary of this problem, you'd say, what values can you plug in to make the equation true? 0 and plus or minus 2.828. What values can you plug in to make the equation undefined? Plus or minus 3. And what values can you plug in to make the whole equation false? Yeah, anything else? I really like writing up my final answer this way because it gives me a nice big picture of that equation. And that is that equation can either be true, undefined, or false. And it's only going to be true if I plug in the numbers 0 or plus or minus root 8. And by the way, only by doing the algebra did we know that 2.828 was actually equal to the square root of 8. Because Desmos didn't tell us that. Desmos just told us a decimal. And then if I plug in plus or minus 3, the equation will be undefined. And if I plug in any other number in the universe, the equation will just be false. All right. Well, what questions would you like to ask about all this, folks? We've been looking at how to solve an equation when there's x in the denominator. So if a friend were to come up to you and say, how do you solve an equation with x in the denominator? What would you tell them? Exactly. You'd say, oh, I never solve equations with x in the denominator. I cancel it out. And then I just solve a normal equation, which is just a polynomial. Anybody? Thoughts, questions? Ask before we keep going? Okay, take a look at the next section then. It says steps for solving rational inequalities. Now, what do you notice about all of these inequalities? What are they asking? They're asking, when is a rational expression what? They're all asking, when is a rational expression greater than or less than 0? And how did we interpret this question again? When we say, here, let's finish looking. When we say, when is this rational expression greater than 0, we're asking, when is the graph above the x-axis? And when we say, when is this rational expression less than 0, we're saying, when is the graph below the x-axis? So all 4 of these questions are simply asking, when is the graph above or below the x-axis? So we're going to answer these graphically together. So we can all sketch a little graph, and then we'll answer it.
So let's start by looking at the first one, 1 over x plus 2. When is this graph above the x-axis? Actually, the question is, when is it greater than or equal to? So when is it above the x-axis? To the right of what? Is that -2? I think it's 2, 4, 6, 8, 10. So that's -2. So when is the graph above the x-axis? Anything from -2 to the right? And when is the graph equal to the x-axis? It does say when is the graph greater than or equal to 0? When is the graph equal to the x-axis? Never, because that's an asymptote. So this asymptote is coming down closer and closer but never touching. This asymptote is coming up closer and closer but never touching. So even though it's saying when is the rational expression greater than or equal to 0, it's never actually going to be equal to 0. It's only ever greater than 0. And it's greater than 0 to the right of -2. Is it greater than 0 at exactly -2? What's the value of the graph at exactly -2? Undefined. So our answer then, we would just write out in interval notation. And everybody, let's draw a graph together. So we're all going to write down graph and a solution in interval notation. So for number 7, we would say 1 over x plus 2 is greater than or equal to 0. Here's our graph with a vertical asymptote at -2. And it's up here or down here. And so we're only interested in this part of the graph up here. And so we'd say whenever x is greater than -2. So on a number line, we'd say starting at -2, but not including -2, and going to the right. Those are all the possible x values that we can plug in. And so in interval notation, that would be -2 to infinity. Does that make sense for the answer? What are we saying? We're really saying, what values can I plug in for x that would make this thing greater than or equal to 0? And you can only plug in values in this set right here. So pick any number over here, and you can plug it into that equation, and it will be greater than or equal to 0. Okay. Questions about that one? Then how about the next one, number 8? Now we're saying, when is x minus 3? When is x minus 3 divided by x plus 2 less than or equal to 0? So I want to know, when is this thing less than or equal to 0? That is, the question is, when is it below the x-axis? So when is this graph below the x-axis? Certainly not anything up here. That's all above the x-axis. Anything to the right of here is also above the x-axis. So we're only looking at this little tail right here, right? So in terms of x values, where is that? It's between here and here. That's when the graph is below the x-axis. So we need to know that point, and we need to know the vertical asymptote. Oh, that point's a 3. And then where's our vertical asymptote? You can tell just by looking at the equation, where's the vertical asymptote? At -2, I'll even graph it just so we can all see it. There's our vertical asymptote. There's our our x-axis, our x-intercept. So when is the graph below the x-axis? Actually, it says, when is it less than or equal to? So it's less than between -2 and 3. And it's equal to at 3. So when we're asking the question, when is this graph? So let's write this out here. When is x minus 3 over x plus 2 less than or equal to 0? And our graph looks like this, where this is 3, and then this is -2. It goes like that. So we know it's between -2 and 3, but do we use open circles or closed circles? I'm gonna make my number line here. That's -2, that's 3. Are they open or closed? The question is, when is this less than or equal to 0? Which one is open and which one is closed? Let's look at the asymptote first. Will I ever actually get to -2? No, so that's open. Will I actually get to 3? Yeah. And the graph is equal to 0 at 3. So this is our number line between -2 and 3. And so our interval notation would be -2 to 3. Now, folks, you'll notice that we're just solving these problems graphically. We're strictly solving these problems graphically. We're not actually doing any algebra. How do you feel about that? Is it okay? Is anyone like, no, Mr. G, let's do it with algebra? Because we could also do it with algebra. But I think graphically is a better and more pleasing solution. And so what would you do that on your test? How would you answer this question on your test? You would need to use your graphing calculator, right? Let's try another one. So x over x squared minus 1. X over x squared minus 1. So we've got our graph here, and we're asking when is it greater than 0? So that is, when is it above the x-axis? So first of all, where's our vertical asymptotes? At 1 and -1. So this is our graph. And when is it above the x-axis? We have this chunk here, and we have this chunk over here. So everybody, let's draw that. Let's draw a graph together. This is number 9. And we're asking when is x over x squared minus 1 strictly above the x-axis? And our graph has a vertical asymptote at 1 and -1. By the way, how do we know that? How do we know that there's a vertical asymptote at 1 and -1? Yeah, the x squared minus 1 are denominator factors into x plus 1, x minus 1, and those are the vertical asymptotes. So you might have to do a little work factoring first, but then that's a vertical asymptote, and that's a vertical asymptote at x equals -1 and 1. So those are vertical asymptotes. And then otherwise, the graph has a asymptotic swoopy down here, and then another one up here. And then the graph in the middle goes up and to the left and down and to the right. And we're asking, when is the graph strictly above the x-axis? So that would be this part and that part. Those are the two parts that are strictly above the x-axis. So as a number line, what would that look like? With -1, with 0, and 1, and infinity. The asymptotes are always open circles. And definitely we're shading to the right of 1. And then here we're going to shade in between -1 and 0. And what about 0? Is it an open circle or a closed circle? We're saying, when is the graph strictly above the x-axis? So that would be an open circle. And that would be our two intervals. So if you plug in any number between -1 and 0, your graph would be above the x-axis. And if you plug in any number bigger than 1, your graph will be above the x-axis. And so your interval notation would be -1 to 0 union 1 to infinity. You'll notice we didn't do any algebra for that particular problem, but there was a lot of analysis. Especially looking at the graph. Questions? So this last one, folks, everybody try graphing it on your own graphing calculator, because that's what you'll need to see during your test. So try plugging this last one, x squared. Using a parenthesis, you type in parenthesis x squared minus x minus 12, divide by x squared plus x minus 6. Everyone go ahead and try that on your own graphing calculator, and I'm going to walk around and I'll help to make sure you have it typed in correctly and that it's working. Your answer should end up looking something like this, especially if you graph between negative 10 and 10. Yeah, that's what you're going to have. So everybody, try plugging it in. I'll just walk around and offer any assistance with your graphing calculator. That's all great. Oh yeah, you got it. Now you'll notice that little line that I have right there, that's just a graphing calculator inability to graph and then come back down and start graphing again. So that vertical line right there kind of represents the vertical asymptote. It's not really part of the graph, it's just a pixel error. So something didn't happen quite right. Well, you need parentheses around your numerator and parentheses around your denominator. Now here, before you delete all that, you can hit second insert INS, then you can insert your parentheses. Then come over and hit second insert parentheses again. And then second insert parentheses again. And there you go, I'll try that. You always need parentheses around your numerator and parentheses around your denominator, and that's correct. Let's see, it's still showing the previous plots. I'm going to go up here to plot 1 and check off. And then here's your graph. We need to choose a better window, so you can zoom. Still graph. We go zoom standard. It'll show you normal left 10, right 10, left 10, right. Doesn't show the whole thing. Oh, you had to turn the color up. Just make that right. Hey, very nice. Now, do you want to see? It worked. Oh, good. Did it graph? Yes, it did. Did it work, Josh? Oh, yeah, so hit zoom and then choose standard. That'll give you the normal.
Try to change the window.
Yeah, good. Yeah, zoom standard, there you go. That's it. Looking good. Yeah. Okay, now folks, a lot of you, when you graph this on your calculator, not all of you, but some of you, your calculator has a pixelation error. Then when it shows you the graph, it looks like that. Because the calculator was literally not able to not draw that vertical line. Because it was going up, 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 and then came straight down, and then up, up, up. So how many of you actually see a little vertical line where the asymptote is? Just know that that's an error. That's a calculator error. It's an inability to not draw the asymptote. So that's what your graph would actually look like. And so then our question is, when is it above or below? When is it above? So when is it above? Everywhere to the left of what? What's our vertical asymptote?
2.
Yeah, 2. Oh yeah, there's just one vertical asymptote and it's at 2. So everywhere to the left of 2, and then between 2 and 4, it's below, so that doesn't count. But then again to the right of 4. So everybody, let's draw that graph together. Now that you've seen it on your graph calculator, let's draw the graph together. Number 10, it had a vertical, I forget. There we go. Our graph had an x-intercept at 4, and it's going up, and it had a vertical asymptote at 2, where it was coming down, and it came up from up here, there. And so the question is, when is this graph? When is this graph above the x-axis? So it's above all of this and only from here to the right. So how would we write that down as interval notation? Anything to the left of 2? So from negative infinity to 2. And then anything to the right of 4, but as an open circle. So anything to the right of 4. Why don't we include 4? Yeah, because at 4, you're looking at the coordinate 4 is 0. And therefore the y value is equal to 0. But the question is asking, when is the function greater than 0? Okay. All right, folks. Well, class is just about over here. When we come back next time, we will finish up the word problems at the end. And then I will also have for you your practice test. So I think I already posted the practice test online. But I will give you hard copies on Wednesday. So when you come to class on Wednesday, I'll give you hard copies. And we'll even have time to go through the practice test. So we'll be able to devote some class time to that. All right. Thank you very much, folks. If you have any questions, please come talk to me. I do have office hours for the next 2 hours. So you can feel free to come up there and ask me any questions you like. Josh. Which one?
The one that we just did.
Oh, yeah.
I had to take a little like it's about like this.
Oh, yeah.
So even though as a level, it's less than
Oh,
that's the way I did it.
oh, well, yeah, there's a hole in.
It's a whole at negative.
Oh, Josh.
I totally neglected to think about that because I was only looking at the graph.
Josh, that's a really good point.
No, you have to change this answer because the hole you cannot plug in.
Yeah, good point, Josh. Let's talk about that on Wednesday. Yeah, really good. Hey, great. Hey, we're gonna go meet? All right, super. And you said you wrote down some corrections?
Yeah, I got it.
All right, excellent. Yeah, I'll be right up. Josh, really good point. That was a subtle problem.
Yeah, I did. It's because I did it without the calculator at first.
Yeah.
I noticed that there was a hole.
Yep, that's a really good analysis. That's definitely a trick question, isn't it?
Yeah.
Take your time.